Okay, thank you, Keith. So welcome, everyone. I appreciate everyone taking the time out of their day to join us for the next hour to talk about streams and flood resiliency. My name is Gabe Bolin. I'm the Eastern Stream Restoration Specialist at Trout Unlimited in Concord, New Hampshire. And today I'll take you through an introduction to basic stream and river functions and infrastructure vulnerability. As most of you know, this is the first of two events regarding streams, rivers, and flood resiliency. The second event being an in-person workshop that TU will host at Duke Farms in Hillsborough, New Jersey, a week from today on December 14. So essentially this webinar is really a primer for next week's workshop. And what we want to do today is provide basic information on stream and river functions and resources and how those resources relate to infrastructure. Both events originated through a Hurricane Sandy grant and project, and both the webinar and the workshop fulfill the outreach portion of that overall project. U.S. Fish and Wildlife Service and the U.S. Forest Service are both the funders and the administrators of that project. So what we'll cover today is, again, basic stream and river functions. We'll talk about the role of floodplains and their importance. We'll then touch on impacts to streams and rivers. Then we'll get to the infrastructure vulnerability assessments. We'll talk about infrastructure improvement and prioritizing those improvements relative to the assessments. And then finally we'll touch on a preview of workshop topics and touch on the agenda. So moving on to basic stream and river functions, we'll start at the beginning with the hydrologic cycle. I'm sure most of you on the call are pretty familiar with this, so I'll just take a few moments and make it quick. But so looking at the image to the left, depending on where your site is and the superficial geology and soils at your site, your soils will have a specific infiltration capacity. During a rain event, when it rains, once the rainfall intensity overwhelms the infiltration capacity, you'll have resultant runoff. That runoff will find its way running overland, running over the surfaces within your watershed, and find its way to the channels that we call streams and brooks and rivers. The water will be conveyed to our larger lakes and oceans, and then through various forms of evaporation, water vapor will make its way up into the air, form clouds, and given the right conditions, we'll have more precipitation. Regarding infiltration, any water that's infiltrated into the soil will either make its way into the shallow ground and probably replenish shallow groundwater sources or percolate deeper into the deep aquifers. So streams and rivers have a number of functions and purposes. Basically, they convey water, so the surface water runoff, subsurface flow, and any groundwater that makes its way into a channel. All that water is conveyed through streams and rivers. They also convey sediment and help to facilitate, I should say, the natural erosion process. They also convey wood, ice, and other matter that's produced within the watershed. And they also do a good job of processing the organic matter produced in the watershed and breaking it down into soluble and insoluble and particulate forms of nutrients like phosphorus and nitrogen and others. And finally, they provide habitat for aquatic and food for riparian life. So a lot of times when we talk about streams and rivers, it's useful to think of them in terms of longitudinal zones. And these two images do a good job of displaying that. So Zone 1, looking at the left, or the picture at the left, Zone 1 is our headwaters. And this is the beginning of our watershed, usually in the hills or the mountains. This is where our streams originate. They are characterized by steep slopes, V-shaped valleys, high velocities. And with those steep slopes and velocities, you typically get high shear stresses and a lot of erosion. So Zone 1 could be thought of as the source of material conveyed downstream. Moving on to Zone 2, the transfer zone. This is where the slopes tend to drop off and become more mild. Likewise, the flow velocities tend to drop off and the valleys broaden. And the material that's coming from upstream typically could be deposited here, but usually is transferred through this zone into Zone 3, where the valleys and the floodplains really kind of open up. The slopes drop considerably, so does velocity, and all that material from Zone 1 just settles out in Zone 3. And because you're at the end of the watershed, your stream discharge is probably at its maximum. Because of that, the channel width and depth increase as well. So similar to the last slide, there is a relationship between sinuosity and slope. And this image, produced by Dave Rosgen as part of his stream classification system, I think does a good job of relating both. So up top here we have a black dashed line that kind of mimics the stream slope, coming from Zone 1 all the way to Zone 3. His stream classifications, A, B, C, D, DA, can be seen above that line, and the dominant slope ranges can be seen just below that line. So just looking at stream type A, we have a slope range of 4 to 10%. So that's definitely up in Zone 1. Those are pretty steep slopes. And you can see, if you look at the plan views below, you can see that a stream type A doesn't really have much sinuosity. It's pretty straight. There's some curves and bends there, but those curves and bends are probably occurring over some pretty long distances, so the relative sinuosity is pretty low. Conversely, if you move over to a stream type E, the third in from the right side, you can see that you have slopes less than 2%, and you have much more sinuosity in a channel like that. Just a couple more items on sinuosity. So there's a couple things I want to relay with this slide, and the first one is that especially in Zone 3, streams and rivers rarely stay put. When you have higher sinuosity, you tend to see migration of the meander bends over time, and that migration can happen from upstream to downstream, and it also could occur from river left to river right. So in order to characterize that and the degree of migration, you can do a channel migration assessment, which is really just an effort in collecting historical aerial maps and tracing the planform or the path of that stream or river during certain time periods, and then gathering those tracings and laying them over each other. And both of these provide a good example of that. You can see in the left side figure from 1939 to 2003 how much the White River migrated, from upstream to downstream and from left to right. And the same in the right figure as well. And the second point I'd like to make here is that degree of migration from up and down and left to right really defines the meander belt width. or the area in which the migration can occur. And that usually happens within what's called the river corridor, which kind of really defines where all this happens. And both of those terms are somewhat synonymous, but more importantly, knowing where that meander pathway is useful not only in planning for any kind of future development, but it could also be useful in assessing infrastructure vulnerability. For instance, and I know this to be the case for a lot of roads and infrastructure, if there's a highway built within the meander beltway and within the river corridor, that road could be subject to erosion if there is migration of meander bends towards the road embankment. So finally, when we talk about stream and river functions, we need to talk about biological communities. And I had just mentioned what a river corridor might look like, and this picture up top does a good job of that. So the corridor includes the main channel, the floodplains on either side, and then any lands that rise from the floodplain up to the edges of the corridor. And this image also does a good job of showing all the potential habitats in the channel and outside of the channel that could exist within a river corridor. But when we talk about biological communities, we talk about two types of ecosystems. One, a terrestrial ecosystem, which exists along the riparian area, and that is directly linked to the soils, the types of soils, and the types of plant communities. And then we also talk about the aquatic ecosystem within the channel, where the biological diversity and species abundance is directly linked to frequency and diversity of habitat. When we talk about habitats in a river or a stream, we're talking about riffles, pools, and glides, and those types of habitat. And they are dependent, their existence and extent is dependent on the stream cross-section shape, slope, confinement, and then also the grain size distribution of the bed material. So moving on to the role of floodplains and floodplain connections. So here we have two images that do a good job of showing the relationship between channel and floodplain. And this is a positive situation. Both of these show a good connection between the channel and its floodplain. And you can see on the image to the left, the flow is all the way up, just up to the top of the bank. Any more flow in that channel, the flow would start to go over the top of the bank and then start to engage that floodplain. And that is typical of a channel that is well connected to its floodplain. Just looking at a real example here, this is Robinson Brook in Stoddard, New Hampshire. So what we're showing here is the green line is showing the surface of the floodplains and the channel. The orange lines are showing the limits of top of bank. And what we see here, this is a good channel that, or I should say, excuse me, this is a channel that is well connected to its floodplain. I would guess that a 1.5-year storm to 2-year storm would probably go over the top of banks and engage the floodplain. So this is a very healthy system. And one point I'd like to make is that when you have bankful flow up to the top of bank, that's the point at which you have your highest velocity and highest shear occurring along the bottom of the channel and the banks of the channel. As soon as you have more flow and that the water surface elevation exceeds the top of bank, and you get flow into the floodplain, as soon as that happens, you get kind of what I call a flow release. You get a reduction in velocity, a reduction in shear stress, and that reduction is one of the benefits that floodplains provide. And I'll show you the opposite case in a couple slides. But let's just touch on benefits of floodplains before we go there. And they're numerous, and I just have a few listed here, but just touching on a few. Floodplains provide for temporary storage space for floodwaters and sediment during large storm events. They're a key component of the river corridor, like we talked about earlier, providing room for rivers to migrate and perform geomorphic functions. So a lot of that meander migration, it occurs within the floodplains, within zone 3. We typically see improved water quality being one of the benefits of floodplains. If you have a floodplain that is forested and full of vegetation like grasses and bushes, that vegetation acts as a natural filter to filter out sediment and nutrients. Once we have that velocity slow down on the floodplain and that water is just basically sitting on the floodplain soils, we can get, there's potential for recharging of the aquifers as that water sits there and infiltrates into the soil. And obviously we talked about that they host terrestrial and aquatic ecosystems, and they also provide for a number of recreational opportunities. So here we go. Let's talk about floodplain disconnections when we don't have that good connection. So looking at the figure to the right, Shum's channel evolution model, we have what's called type 1, which is stable, and that's similar to what I showed a couple slides back at Robinson Brook. The channel is well connected to its floodplain. It can reach the floodplain probably at the 1.5 to 2 year storm event. When we get to type 2, we get to something called an incised channel. An incision refers to when a river or a stream has cut downward through its bed and has become disconnected from its floodplain. Now that's pretty typical in headwater streams in zone 1, because typically you have steep valley walls and the water can't really go anywhere. It's very confined. So the channels in headwater streams cut down. That's pretty normal. But incision in say zone 3 typically occurs due to anthropogenic sources or human causes. And usually when you're mining a channel bed for gravel to use that gravel somewhere else, you're cutting down. So that's a source of incision. Flow increases due to development can cause a channel to incise, and then channel straightening, which we'll talk about in a moment, also can cause incision. But getting back to the figure here in type 2, when that channel drops and the top of banks remain stationary, the banks become nearly vertical and unstable. And what happens as we move to from type 3 and 4, because the flow is contained in that channel, say like the 50-year or the 100-year storm isn't getting out of the channel, there's no flow or energy dissipation because it can't get onto the floodplain. We're really capturing a lot of that energy, and that energy is working those banks and eroding the banks that are already unstable. So you get this new source of material entering the channel, and you go through stages 3, 4, and 5. And you can see in stage 5 that you end up with a channel that's actually now connected to a floodplain. The floodplain is much more narrow, but there is a floodplain. And this is Mother Nature's way of trying to find some kind of equilibrium. So here's another example from the field of a channel that was actually straightened. This channel was, years ago, there was probably a machine in this channel that took all the sinuosity out of the channel, probably made it deeper. There was evidence of berms along the top of bank, all along this reach. So they dug down, dropped the bottom of the channel, created berms so it wouldn't flood onto the floodplain anymore. So it's a perfect example of man-made incision. And then what we're seeing out in the field is a good example of it progressing through this channel evolution model. Based on our field data and observations, we believe this reached to be in a type 4 or type 5. And you can see from my outline of the surface of the floodplains in the channel, there are, or I should say there's evidence of this new kind of inset floodplain that this channel is slowly forming. So let's move on to talk about impacts to streams and rivers. And we're going to stick with this project, this channel that has been straightened. And if I haven't said it before, the name of this stream is Spring Brook, located in Hector, New York, just off the Finger Lakes National Forest. So in the image to the left on this slide is just a standard Google hybrid map showing Spring Brook flowing in the northeasterly direction. The path of this stream is consistent with historical maps. So what we did is we traced it and superimposed it as this light blue line on the aerial to the right. We then traced the channel, the existing channel as it exists today, and traced it according to where we know it to be, and came up with this line in orange. And it's pretty clear that this channel was straightened probably 50, 60 years ago, we suspect, to kind of behave and coincide with property boundaries rather than running through the property to the north of that obvious farm in the aerial. So that's a big change. That's a huge impact to a stream system, and we're seeing the effects of that today. What's also interesting is if we zoom into that orange oval that I have on that map, you can see the former channel running through that property. And you can also see the existing channel on the bottom of that image. And if you take a picture of that, this is what it looks like. This is the straightened channel looking downstream. And it's the impacts are significant. You usually, with a lot of this straightening, you usually end up with what's called a plain bed, which really doesn't have much complexity to it. You can see the bottom is just flat. There's no thaw wig, or there is, but it's very slight. You can also see downstream about 50 or 100 feet, there's some gravel bars forming on the left side. There's one on the right side as well, and that's, Mother Nature trying to find, trying to recover that sinuosity and trying to find some equilibrium. But at this point, without human intervention to fix this, it could take 50, 100, 200 years to recover. So moving on to other anthropogenic or human-caused impacts, encroachments are pretty common. If we look at the image to the left, this is a culvert replacement project that we finished constructing in 2016, in summer of 2016 here. And there is a pretty obvious encroachment. Somebody put in a large amount of material in this floodplain to kind of train this stream to head in a certain direction. And we did not remove that material because 50 years later that stream is actually pretty stable. But we see that a lot. And then in the pictures to the right, we have a house built in the floodplain. Years ago this was very common, and unfortunately people today are still building structures in the floodplain. That's a reduction in flood storage volume. It's not a huge reduction, but it is a reduction nonetheless. And what it also does is it puts people and property in harm's way. Urbanization, starting with the image to the left here, in the upper left, for a natural condition during some degree of rainfall, we see that 10% of runoff, or 10% of that volume is runoff, 25% of that rainfall volume is shallow infiltration, and 25% of that rainfall volume is deep infiltration. And this is for a natural ground cover. So not a whole lot of runoff. If you go down to the lower right, after we've built our houses and our skyscrapers and paved roads, now we're looking at, for a certain rainfall, 55% of that rainfall volume being runoff, 30% of evapotranspiration, 10% shallow infiltration, and 5% deep infiltration. And those, percentages correspond to impervious surface cover of 75 to 100%. So when you look at both extremes, we have a 45% increase in stormwater runoff. And when you send that increase in stormwater runoff to a stream or a river, what happens is the stream is just going to adjust. It had a certain cross-sectional area, and it's going to widen or deepen or both, basically adjusting its cross-sectional area to adjust for that increase in flow. And that could take 50 years or 100 years to occur, and it could also be a steady source of sediment while that adjustment is occurring. So looking at the images to the right, the one up top, that was a kind of a conceptual model of stream quality versus watershed impervious cover developed by the Center for Watershed Protection out of Maryland. And basically that image was kind of referenced for years in the watershed and TMDL world, basically stating that 10% impervious cover was kind of a sensitive point. If you had less than 10% impervious cover, your stream condition was good. If you had greater than 10% impervious cover, you were in some kind of impacted status where you had either fair or poor stream quality as watershed impervious cover increased. Looking at the image to the bottom of that graph is another plot of RGA, which is a measure of stream quality, versus TIA, total impervious area. And this is from a paper published in 2012 by Evan Fitzgerald, a geomorphologist in Vermont, Mike Klein, head of the Rivers program at Vermont A&R, and a couple other authors, basically using a lot of the information that they collected while they conduct many stream geomorphic assessments. And for high gradient reaches, what this graph tells us is that there's a pretty precipitous drop in stream quality as impervious area increases. And to note is that really the inflection of that curve could really be interpreted at 5%. So less than 10%. But either way, anywhere from 5 to 10% could be a point at which the scales start to tip and our streams and rivers are negatively impacted. We have some other anthropogenic-related impacts to streams that I'm listing here. Obviously, dams are really at the top of the list. Any type of road crossing or railroad crossing or utility crossing is an impact, and we have others that are high impact as well. There are natural impacts to streams and rivers. A lot of those are related to large storm events, high flow, and high shear stresses. The example that we're looking at to the right is kind of a mass failure along a bank in a pretty large brook in a pretty wild system on the White Mountain National Forest in New Hampshire. I believe this was caused by a large storm event, high flows, high shear forces, and eventually a mass failure along this bank. So we talked about basic stream and river functions, the importance of floodplains, and then the impacts to streams and rivers from a number of different sources. So let's change gears and focus on infrastructure, and specifically infrastructure vulnerability. So at Trout Unlimited, and I don't mean to speak for them, but I think at U.S. Fish and Wildlife and the Forest Service, I know that we're really into streams and watershed and fish. And I know the question could be from some of you is why the focus on infrastructure and flood resiliency? Why are we focused on that? Well, one thing that we know and what we've discussed over the last few minutes is that infrastructure often impacts rivers and streams. It has in the past, and it's happening right now. But the opposite occurs too. You know, rivers and streams impact infrastructure. I think maybe half of us on the call and who will be at the workshop will be very interested in the rivers portion, and maybe the other half might be interested in the infrastructure. But what we found through our work focusing on dams and culverts is that not everyone is into rivers and fish, let's face it. But most of us are into flood resiliency. You know, most, if not all of us, want to get through the next natural disaster or large storm event with minimal impact and minimal losses. And that's something we all have in common. So the people that are interested in the physical natural resources, the biological natural resources, and maintaining infrastructure and building good infrastructure all have a common goal. We have a nexus. And what we have found in our work is that restoring hydraulics often improves fish passage and geomorphic compatibility as well. So there's a nexus for us to follow, and that's one of the main reasons why we're here and that we're going to meet next week. So talking about infrastructure vulnerability, there's a number of examples. Again, I try to list these things, but let's face it, you can never list every example. These are just a few. Aging and outdated dams, again, it's at the top of the list. The state of Massachusetts, their last count that I'm aware of in terms of low-head dams in the state that don't really have a purpose anymore is about 3,000. And really, those dams are at this point just a liability to the owner. Next, undersized road stream crossings. It's a big focus on our end. And there are it seems almost an endless amount of them throughout New England and I'm sure throughout New York, New Jersey, and Pennsylvania. Roads constructed along or within river corridors. I tried to touch on that previously. That's another one that's worth a look for the planners out there and anyone within a town that wants to assess those types of vulnerabilities, and then infrastructure adjacent to cleared lands or deforested lands, adjacent to or downstream with floodplain losses or encroachments, and an improper bank armory, and the list goes on. And the list goes on. So what we're going to do is, we don't have the time to go over more than one example, unfortunately, at least for this. We'll try to touch on other examples in the workshop. But for the remainder of this presentation, we're going to focus on undersized road stream crossings. So the image, what we're looking at here is the long kind of rectangle in the center of the screen is an undersized culvert. There's a road on top of that culvert, and you can see the roadway center line. The stream bed is underneath that culvert with kind of that dashed hatch underneath. And so let's just imagine that this undersized culvert is at the bottom of a large watershed. The 100-year storm event has just occurred or is in the process of occurring, and there's a large volume of water heading down the mountain towards this undersized culvert. In its path, it's stirring up sediment, gravels, cobbles, maybe some boulders. The majority of that material is entrained in the water column, and there's enough energy to keep that material in the water column. As that water moves down and kind of feels the influence of that undersized culvert, all of a sudden that mass of water slows down. Okay, as it slows down, it gets backed up, and the water surface elevation starts to rise, or there's basically flooding behind this pipe. Because it's slowing down, the velocity is dropped. And because that velocity is dropped, the energy is reduced, and everything that was entrained in that water column is now settling out. So what we see typically upstream of an undersized culvert is what we call the sediment wedge, or just this collection of settled sediment that I'm trying to depict with a green polygon. Downstream, we usually have the opposite case. We usually have water surface elevations that are relatively lower compared to upstream. Because of the pressure upstream, we have a fire hose effect on the downstream end with really high velocities coming out of that pipe. And because of that, we have sediment erosion. And it's not just along the bed. In a lot of cases, it's around the entire pipe. And this is a good example. This is the Meadowy River in Dorset, Vermont. What we've seen, especially with corrugated metal pipes that kind of project from the road embankment, we see severe erosion around the pipe. And from what I understand, during a high flow event, when you have that pressurized flow, you have eddies kind of forming around the edges of the pipe, not only at the bottom of the pipe, but all around the pipe. So you tend to get erosion around the entire radius of the pipe. And there is a road on top of this pipe, and I would say that this pipe and road and stream system is pretty vulnerable overall. So what we do in these situations, and what us and others in New Hampshire, Vermont, Maine, Massachusetts, we do culvert assessments. And I'm sure these are being done in Pennsylvania, New York, and New Jersey as well. But I'm going to walk you through a culvert assessment. This is one of our projects that I'll share. So what we're looking at here is this is our Ammonoosuc River Stream Crossing Assessment Project. We're doing this in partnership with Plymouth State University in Plymouth, New Hampshire. This watershed is located in northwest New Hampshire along the Connecticut River. There are 23 towns in the Ammonoosuc River watershed, 742 road stream crossings, depicted by red and green dots on the map. And these crossings, there was information collected on these crossings, and they were assessed for geomorphic compatibility, aquatic organism passability, or aquatic organism passage, otherwise known as AOP, and then hydraulic capacity. So one of the first steps when we do one of these is we start in the office. We open up GIS and we bring in all the road layers, we bring in all the stream layers, and wherever those intersect, we assume that there's a road stream crossing. And then we get volunteers and TU chapter volunteers, grad students, other people interested. We usually team with universities and partners that provide volunteers as well. And over, say, a summer season, we send people out to collect data on these crossings and run them through the geomorphic compatibility, AOP, and then hydraulic capacity. I should also say that those three models are Excel-based models. The geomorphic compatibility and AOP models, I believe, originated in Vermont and were adapted for other states. The hydraulic capacity model didn't exist as far as we know, but we worked with a partner to create it in 2012 to assess the ability for these culverts to pass certain storm events. So in terms of data that we collect, and this is just some of the data, but we collect structural data, geomorphic data, and then fish passage data to support the three different assessments that we go through. And we also collect survey data shown in the image to the right. And then we run that data through the aquatic organism passage and geomorphic compatibility models, and we get various results. So for AOP on the left here, we have results ranging from full AOP to no AOP to unable to score, for some reason, which is a small percentage here. So for example, for full AOP, we get 38 crossings had full AOP, and 143 had no AOP, including adult salmonids. So no fish are getting past 143 of these crossings. And 176 had reduced AOP. For geomorphic compatibility to the right, again, we go through the full gamut here: fully compatible, partially compatible, and then incompatible or unable to score. So those are the basic models that existed, and we went ahead and created this culvert hydraulic assessment model. As you would think, this effort includes collection of a good amount of hydrology data. Basically, you have to collect hydrology data for each culvert, right? And that's primarily a GIS-based effort. And then for hydraulics, we used the information collected from the field effort. Both those sets of information are inputs to this Excel-based model that's been created, and then we assess the passability of these occurrence interval storms. This is an image of the tab where you're going to input all of your hydrologic data. Okay, so drainage area, curve number, 24-hour precipitation for a bunch of different events is shown kind of to the left. As you move to the right, just kind of follow the blue shaded information, that A1, A2, A through A. Those are the culvert IDs, and you can see each culvert has specific hydrologic information. We move on to the tab where you input the hydraulic data. Again, you have certain culvert properties. You have a reference number, a length, an inlet and outlet elevation, roadway elevation, a rise, a span, again, for all the different types of culverts. And once you have that information input in, then you go to the Results tab. If this was live, I would go ahead and select the return period. Here we have a 100-year return period. And kind of in the first section we have looking at the text that's kind of at a 90-degree angle, existing crossing properties. So you have all the existing properties for each culvert ID. Again, those are listed as LP, BOB, KO2, and so on and so forth. And you can see that there are cells shaded red, green, or yellow. And those are the results, basically telling you, was this culvert able to pass the 100-year storm event, or was it not? So the basic way that this model is set up is that it uses what's called the headwater to depth ratio to assess whether it passes, is transitional, or fails. So the headwater is basically the depth of water just upstream of the culvert, and the depth is the height of the culvert pipe. So if the height of the water upstream of the pipe was 0.8 feet and the culvert pipe was 1 foot high, you would have a headwater depth to depth ratio of 0.8. And the way we set up the pass or fail in this model was that if the water was greater than, had a headwater depth ratio greater than 0.8, it failed. If it was between 0.8 and 0.65, it was transitional, and if it was under 0.65, it passed. So that's how we set up the pass-fail mechanisms. What we should also say is that in order to generate the hydrology, embedded in this model are the USGS StreamStats regression equations. We use those equations to generate flows for certain type watersheds or certain size watersheds. Anything that was under a certain size, we just used the NRCS method of developing peak flow. So there are some details in here that provide more explanation, but I think we'll leave it at that for the purposes of this webinar. We're going to touch on this more in the workshop. So finalizing our infrastructure discussion with improvements and prioritizations. So once we would go through all three of the models and had an idea of geomorphic compatibility, AOP status, and then an idea of which storms passed the hydraulic model and which failed. This is kind of a report card that we would give to each town in the watershed. So this has the road name, the stream name, crossing ID, and then all the way to the right from the initial models we have AOP status. So if something is red, that means there's no AOP. If it's gray or orange, it means there's partial AOP. And then we tacked on the results for each return interval storm event, pass, transition, or fail. And this, along with maps, and I'm going to zoom in here, are a tool that the towns could use to say, okay, how do I prioritize the replacement of these culverts? So again, using the table we just showed and then these maps, which I personally think are more useful, they could say, okay, well, this culvert is on the road that leads to the police station or to the hospital, and it doesn't pass for the 10, the 25, the 50, or the 100. So let's put that one at the top of our replacement list, whereas other ones that might be lined up with some kind of development that doesn't have near as much priority might be on the bottom of the list. So we're going to stop it there. I'm running out of time. We are going to touch on that in more detail in the workshop. But let's go ahead and just touch on a preview of the workshop topics. Everyone going to the workshop will receive an agenda, if you haven't already, along with directions and some other information. But this is kind of a summary of the agenda. So we're going to start off in the workshop with another presentation that's going to be slightly different, that provides an introduction to streams and rivers, and then the role of infrastructure. Similar to this presentation, but again, a little different. And we thought some repetition on what we relay to you would be useful, thinking that repetition is the way we learn, and there's some important points there that we're trying to make. In other words, if you walk away knowing that streams and rivers are sensitive and have a unique relationship to infrastructure, if that's all you take home with you, I think that's a plus. We're going to follow that up with a discussion on certain types of infrastructure improvements that you can make to increase flood resiliency. And then we're going to have a discussion on the role of wood in streams and other infrastructure or green infrastructure improvements that you could make to improve flood resiliency. FEMA will be present and talk about funding programs that are available and steps that you can take to apply for even more funds related to flood resiliency projects. They'll also talk about the community rating system, or basically the system that communities can go through to improve their flood resiliency and reduce flood liabilities. The New York State Delaware County Soil and Water Conservation District will talk about their local flood analysis programs and talk about their post-disaster stream intervention. So that's when we get into what to do and what not to do following a large event in relation to streams and rivers, and make sure while we're cleaning up after an event we don't harm our natural resources. We'll then have a discussion about the Vermont A&R Rivers and Roads program and a lot of the trainings that they put on within their state for DOT and other agencies and people involved in this type of work. And then we'll have a panel discussion, wrap that up, and then the Duke Farm ecologists will host the field trip to the on-site wetland restoration project. And just one more slide, one more thing to relay to you folks is that feel free to spread the word. One of the things that we were required under this grant was to not only have a webinar and a workshop in New Jersey, but we are also going to have a similar webinar and workshop in Massachusetts in March of 2017. The goal was to try and cover all of the Sandy states, or at least some of them, and provide this information in most of the states that were affected. So we'll have this event again in March based in Hadley, Massachusetts. So that's about it. Why don't we go ahead and open it up to questions. There's been a number of questions that have come through in chat, and I've selected some and we'll try to answer them.